Hello, everyone. Yeah, okay. My name is Gokul. I work at Cask, and I'm going to talk about transactions in HBase. Andreas is also my colleague, who's also an author on this particular presentation. So, a brief overview of what you're going to talk about. We're going to talk about why transactions, what is the motivation behind having transactions on HBase, and then we'll talk a little bit about the optimistic concurrency control, higher-level overview, which is probably the main idea behind the 3 Apache projects. We're going to talk about Omid, Tephra, and Trafodion, which are all 3 different Apache projects which try to address this issue in slightly different ways, and we're going to just compare and contrast between the 3 and among the 3, and we'll get a little bit overview of how they work. Just a brief history of what about transactions in NoSQL. We started with SQL, and now when we went to NoSQL, they were really transaction was never in a picture, but then it kind of evolved to NoSQL kind of evolved to not only SQL, where you had Hive or Phoenix, tried to provide a SQL interface. And also it started to, in order to operationalize some of these big data workloads, transactions sometimes also becomes important when you want to have data consistency under very highly concurrent loads. And sometimes, let's say, for example, if you have partial outputs, and then after suddenly there is failure and you have partial outputs, how do you make sure that the clients who are reading it or they don't see partial writes? And also sometimes it also helps enable near real-time processing frameworks. We'll kind of look into one use case later. So, for example, at Cask, one of the the paradigms that we provide for real-time processing is called flows, where you have you can think about a directed acyclic graph, and a flowlet is one of the processing nodes. It kind of dequeues elements from a queue, which is also sort of implemented on top of HBase, and then does some processing, writes to modify some state in HBase table, and then just write some output to the subsequent flowlets to read from. And then you have to implement all of these in like the dequeue from the queue, your processing input queue, and then modifying the state, and then writing to an output queue. All of this needs to happen atomically, and also you also want to prevent from another processing. Another flowlet trying to access the same data and trying to modify the same data at the same time. You want to prevent that as well. And so this is where transactions becomes very useful for us, where we want to make sure all these operations are done atomically, and also it prevents from concurrent update. Like, for example, when we saw in another case where another flowlet was, let's say we take a simple example of an increment, where one flowlet is trying to read a value, increment it, and then write it back, while the another one trying to do the same thing, and we want to allow one of them to succeed, another one to kind of retry, and that is where we kind of use transactions. This is one of the use cases for transactions. And we all kind of know about what the asset properties are, which are from the SQL world: atomic consistency, isolation, and durability. Not all of these are provided out of the bat for HBase, and we will try to kind of look into how we provide the complete asset property using Tephra and Trafodion and Omid. I'll skip through what is HBase slides. There's a couple just for introduction for the other audience. For asset properties, for example, for atomicity, HBase provides atomicity at cell or row level, region level, but not when it comes across regions or multiple tables. It's not really atomic. And for consistency, there's really no inbuilt mechanism. So that means, let's say I write to cell A and then I write to cell B. There's really there's no way to prevent partial writes, for example, in case of failures. So that's where consistency. That's the consistency I'm talking about here. And then isolation, there is some level of isolation that you can provide using timestamp filtering, but not completely. And durability is something that's all provided by HBase, because once committed, the data is persisted. So implementing transactions, the traditional approach in the RDBMS world was to use locking, where you lock the different rows or cells that you want to modify. But then what happens is sometimes it might cause deadlock, and it's also very hard to implement distributed blocking. That's where we come into optimistic concurrency control. It's a lockless way of implementing allowing concurrent writes to proceed at the same time. And when there are multiple writes that are happening at the same time, while at the commit time, you kind of figure out if there are any conflicts, and then with other transactions, and if there is a conflict, and you roll back the one that is trying to commit later. And so what this kind of builds on top of is, for example, hopefully there are not many conflicts, and if there are, you pay the price of rolling back and then trying to retry the operation. And in terms of isolation, it provides, you can think about snapshot isolation. It's sort of similar to repeatable reads, where when a transaction starts, it gets one snapshot view of the data, and then that is only visible, and if there are any writes that it does, it's visible to itself. And so that's snapshot isolation. And this is just a kind of an overview of optimistic concurrency control. This is just a timeline. Or you can imagine a client 1 starts its transaction and then writes, let's say it sets writes value of x to be 10. And after some time, client 2 starts, and when it tries to read the value of x, now what it will see is the old value of x, because the client 1 has not committed its transaction yet. And for example, it might just fail, in which case, what client 2 actually saw, which is the old value, is the right thing to do. And let's say the client 1 rolls back and the client 2 commits, and it's all good. Now, in the case of modification, when let's say client 1 starts and then increments the value of x, and then client 2 starts and then it also tries to increment the value of x, but then client 1, when it tries to commit, the system the transaction system allows it to commit because there was really no conflict. But when client 2 tries to commit, it has a conflict because client 1 had already committed. It has, and then they both were trying to write to the same cell, same value, and so same key rather. So in that case, there is a conflict, and the transaction system identifies that, and it says that for client 2 you cannot commit, and then you have to kind of roll back your write, and it can retry again. And in that case, when client 2 rolls back and then retries and tries to read the value, in that case it'll see 11, and so it's able to increment and then persist the new data, and so that kind of gives you the right answer. So this is different scenarios that could happen. Let's say transaction, these are all different transactions. So when transaction, they're all modifying an overlapping set of rows, let's say, or for simplicity, you can assume that they are modifying the same key. So transaction B completes, transaction A completes. Because transaction B completed before transaction A is also just works fine. It's able to commit without any problem. In this case, transaction C started before transaction A and then commits before transaction A does. So in this case, when transaction A tries to commit, it fails. Similarly, as you can see that in transaction D, even though it started after transaction A started, but it committed before transaction A did, and so when that succeeds, but transaction A, when it tries to commit, it fails, and so on. So basically, the idea is that the committing point is when what matters, and then we try to, we roll back the transaction that's tried to commit later. So just to summarize, so when you have two transactions have a conflict, if they are writing to the same cell and then they overlap in time, and the one that tries to commit later rolls back, and then there is a concept of the active change set. This is what we have in this is what you hold in memory to figure out if there is any how do you detect a conflict. And so you have these are the transactions that have committed, and then there is at least one transaction that is in flight that started before the commit, and then you have that set so that you detect conflicts. And then this is the concept by which, this is a higher level overview of optimistic concurrency control, and 3 projects that have implemented. We'll go through one of them one by one. And so as we discussed before, they have certain things in common. What they have in common is the optimistic concurrency control implementation. So somewhere we need to maintain this transaction state of what are the transactions that are in flight, what have committed, and what is the change set of each transaction. And there are certain cases where you also want to maintain the transactions that have been invalidated. And because when, for example, the client just crashed and never really committed or rolled back the transaction. And they also you have to also generate these unique transaction IDs, and you have to coordinate the lifecycle of a transaction. We'll look into the lifecycle a little later. And so we'll go into Apache Tephra, which is what I work on. It's based on an original Omid paper. So here what we have is a transaction manager. It issues unique monotonically increasing transaction IDs. And then it also maintains a set of excluded, like invalid transactions and in-flight transactions and invalidated transactions. And it also maintains the chain set of active transactions that we talked about, so that it can detect conflicts with other transactions that are trying to commit. And the transaction manager itself performs the conflict detection. And in this case, the client uses the transaction IDs as a timestamp for writes. And it also filters the transaction for isolation. So for example, let's say it reads the data, and then for example, it needs to filter out ongoing in-flight transactions. It does that as well. And in case of invalidated transactions or rollback, the client has to perform the rollbacks as well. So let's say we started new transaction. It's marked, this transaction is marked as in progress, and then the clients write to HBase, and then when they try to commit, the client goes to the transaction manager. Someone say, here are the changes that I've done, can I commit? And the transaction manager detects that hey, there are no conflicts, so you can go ahead and commit. And so in that case, the transaction is made visible for the rest of for the new transactions that are starting from now on, it will be made visible. Let's say if there is a conflict, there was previously a transaction that wrote to the same rows or row keys, and so then they were successful, and so this transaction needs to be, the current transaction is having a conflict, so it needs to abort. So the transaction manager gives that information, and so it rolls back the changes that it did in the HBase, and then it's all good. But there could also be a possibility that the client failed to roll back all its changes. So in this case, this transaction is added to the invalid list. So this is always the data that's written using this transaction ID will become invisible for all the other future client operations. And it's also possible that the client, after starting the transaction, just times out. It never really responded, and in that case, after the transaction timeout period, then the transaction manager will move the transaction to an invalid list. So this is, we'll just walk through an example. It'll become a lot more easier. So let's say client A starts a transaction, and the transaction manager provides it an ID. Let's say the transaction ID is 42, and it has it in. It also maintains that in the in-flight list. And then the client A. So this is what the data is for x value of x is 10, and that's a timestamp 37. Client A writes the new value of x to be 11, and that's with the transaction ID of 42. And it also, let's say, writes the value of y to be 17, the same transaction ID. Client B comes in, starts a new transaction, and then it has 42 in its exclude list because that is in progress, and tries to read value of x. Now, the previous client has not really committed, the client transaction ID 42 has not committed it. So that is in the exclude list. So when it tries to read, it gets only the value of 10. That is a previously committed a visible transaction, the value that is 37. And that is what is visible to the client B. And let's say when client A tries to commit, and then it transaction manager for some reason says there is a conflict and you need to roll back, it'll just revert back the changes that it did to it in the HBase table, and then it says, hey, I've done the rollback, and so I can make it visible, and so it has removed the changes that it has made. Or it could be the case that the transaction client A succeeds in committing the transaction, and in which case when another client comes in later after the transaction, client A committed its transaction, and client C starts its transaction, and it tries to read the value of x. In that case, the client A's transaction ID is no more in the exclude list because it's made visible, and so the value of x will be 11 in that case. So the transaction manager in this case, as we saw, maintains the transaction state. It does the ID generation, while the client maintains the lifecycle operations and also does the rollback. Tephra also makes use of HBase coprocess for a couple of things. For example, first is filtering. So the filtering operation that we saw earlier, the coprocess can just do that based on the transaction state. And then we also use that to remove invalidated data. So for example, there were certain scenarios where, for example, the transaction could time out. In those cases, during compaction, we'll just remove that in data that was written by invalid transactions, and we'll remove that from HBase. And so that's where we use HBase coprocessors. And then the programming abstractions, won't go into a lot of detail of this, but it provides it provides a transaction htable, which implements the htable interface. So it's easy to kind of use their existing code and to port it easily. And just a simple example that you can look at, and it's kind of has, I mean, we want to make sure that the programming model is easier and it's very similar, same as the htable model, so that your client code is just easier and simple to plug in Apache Tephra. And some of the strengths, it's compatible with existing non-transactional data, and then you have the conflict detection granularity is up to the clients, so you can figure if you want to do row-level conflict detection or column-level conflict detection. It's up to you, the clients. The transaction manager really doesn't care about that. It just uses I know, the byte array as an identifier and then detects conflicts. Support replication, HA, and fault tolerance. The transaction manager writes the changes of transaction state to write-ahead log. So in case of failure, it can recover pretty fast. And it's kind of secure and supported in multi-tenant environments as well. And there are certain not so much of a strengths. For example, the transaction invalid list can kind of grow quite a bit. And there's also another bottleneck of the single transaction manager, because right now we just support a single transaction manager, and it does all the lifecycle transitions, conflict detection, and sometimes it might become a bottleneck. The solution is to kind of go to a distributed transaction manager with the consensus protocol, and that's still it to be implemented. It's still but it's on the roadmap. Now going on to Trafodion, it's a completely distributed database. I will go through this a little more faster. The API that's provided to you is more of a JDBC SQL interface. It doesn't. The transaction management part doesn't come separately. It comes just coupled tightly with the distributed database model. It was inspired by the original HBase transaction region server, if people remember that. And then here in this case, the transaction manager orchestrates the transaction lifecycle, but also it uses the region servers, and the coprocessors in the region servers actually do quite a bit of the it maintains it does the conflict detection and also maintains the transaction state. And so in this case, the transaction manager here, you can also have multiple instances, and all the transaction manager does is it just issues like a two-phase commit where you can check with all the different coprocessors whether it can actually, if there is a conflict or not, and then receives all the data back, and then it just decides whether to commit or roll back the transaction. So it'll become a little more clear while we walk through the diagram flowchart. So in this case, a client A starts the transaction similarly, and so it gets transaction ID of 42, and then the client tries to perform a write where, in this case, the value of x in HBase is 10. Now the client wants to write the value of, it wants to update the value of x to 11. Now in this case, instead of persisting that to HBase directly, this yellow blocks are actually a coprocessor in-memory state. And so this write is intercepted by the coprocessor, and it holds that new data in its memory until the transaction is actually committed. So here we have the value of x to be 11. And it writes another value of y is equal to 17. It's probably in another region server. Now client B starts another transaction which has a ID of 48. Remember that the other transaction is still in flight. And so when it tries to read the value of x, what happens in this case is it actually reads only the committed data, and so that it actually gets the value of x to be 10. And then when, let's say, client A tries to commit, the transaction manager doesn't perform a conflict detection itself. It just asks all the region servers, hey, are there any conflicts? And so in this case, let's say the region server, it gets back a conflict, and so it'll just ask the region to just roll back the transaction, and so it'll remove it from this in-flight. So in that case, it's just a removal from the in-memory state. And let's say in the case where it actually succeeded in committing, in that case, just the in-memory state is just transferred to the, and it's persisted in HBase, and so the value is updated. So in this case, what happens is, as you can imagine, the transaction ID generation is actually done by transaction manager itself, and the lifecycle management is done in the client side, and the transaction conflict detection and all the in-flight data management stored done in the region servers and actually by the co-processors themselves. So this is, and also just to note that you can have multiple transaction managers running, but the client talks to only a specific transaction manager. So with this architecture, what's good about this architecture? It scales pretty well. The conflict detection is not done by a single transaction manager in the sense that it's actually distributed, done by each of the respective co-processors. All the transaction manager does is just the coordination among these different co-processors. And there's also some optimization that you can do if it's just going to one single, if you know that all the changes are going to one single region. The co-process actually cache the in-flight data in memory. And so it's only flushed to HBase only on the commit side. And so, and the reads are actually, you can only read the committed reads. There is also an option where, let's say if you, there is also a possibility that, for example, when you are trying to read a data, for example, one of the co-processors that you're trying, one of the co-processors actually moved the data to HBase, one of the writes has been moved to HBase, but the other one is still in memory. There is a possibility that you might see one committed data and one as a non-committed data. So that's a problem where, in that case, your reads transactions are also will actually conflict. So in this case, you have a read-write conflict. So you'd be aware of that operation as well. Otherwise, you might, if you're okay with reading some inconsistent data, then it's probably okay. Then in that case, you won't get a conflict detection. I think it's something that you can configure. And then they use write-ahead logs for maintaining all the state. And so in case of recovery, they'll just use the write-ahead log to replay and get the in-memory state or the in-memory co-process state back. And they also have a replication support, and I think that's only the it's in the non-Apache. It's a paid version. It's an add-on feature. Some of the strengths, it's pretty really scalable. It's and then it's familiar SQL kind of interface. And then some of the not so much of a strength is basically that it's tightly coupled to this JDBC or the SQL layer, and so you have to get the whole distributed database or nothing. And it also, as you can imagine, so there's a lot of load on the co-processors, a lot of memory and compute. And in cases of large transactions, for example, if you're writing a MapReduce job that writes gigabytes of data, all that data has to be held in memory in the co-process before the entire operation kind of commits. So there's really no large transaction support. There is a possibility that it will go out of memory. Then finally, we come to Apache Omid. We'll go through this a little quicker. And so here the idea is that they've tried to make the transaction manager as lightweight as possible. So they moved much of the transaction state into the HBase itself. And so, for example, in this case, every cell that you have maintained in HBase as a shadow cell, and that maintains a state of what data is actually visible, and so whether that actually the data is visible or not. So that transaction state is maintained per cell, and it's maintained in a shadow cell in HBase itself. And there's also a commit table which maintains the overall transaction state as well. So we'll quickly go through this example. Well, let's say client A starts a transaction. Transaction ID is 42. The value of X is 10 in HBase. And this was written by a transaction that started at timestamp 37 and committed at timestamp 40. When client A writes the data, it wants to update the value to X to 11. And then it writes the new data, and then it writes the transaction ID, and then marks basically doesn't have a commit timestamp, so it's actually in flight. And then does the same thing for another the same client using the same transaction ID does another update to another region server. Now a client B comes in and then starts a transaction and wants to read the value of X. In this case, it'll just see these two versions, and it figures out that 42 is still in flight. It's not yet committed, but it looks at the previous version of the cell, and in that case, it's actually 40, the transaction ID, which is already committed, and that has been committed before the transaction client B has started its transaction, which is 48. And so it can read that value and gets the value of 10. And now, for example, when client A wants to commit its transaction, it goes to the transaction manager and says, I want to commit. In that case, if there are no conflicts, the transaction manager actually writes that the client, the transaction 37 was committed in the table. So for example, let's say, for example, client A tries to commit and then it gets a rollback. In that case, it's pretty similar to the Tephra's case where the client will actually roll back the changes that it did. In the case where client was successful in committing the transaction, in that case, it writes it to the commit table. This is also another table that's maintained in HBase with the start time stamp and then the commit timestamp. And then it also marks the all the data cells where it has actually made a change. It'll just go and mark that the commit timestamp of that particular cell. So now when another client comes in and tries to, if it starts a new transaction with client ID 52, tries to read the value of X. In that case, the first version of X that it sees has a value of 11, and its commit timestamp is 50, which is before its timestamp. So it reads that's a visible version of that cell, so it reads the value of 11. So overall, like for example, in this case, the conflict detection right now happens in the transaction manager, and the transaction ID generation is also done by the transaction manager. And here, as you can imagine, there is few things that are different. For example, the transaction state is stored in the HBase itself. So that means there is these shadow cells adds a little more of storage requirements. And there is also they have also implemented fault tolerance, where in the case of failure, they will fail all the existing transactions that are currently in progress, and they're trying to attempting to commit. And so there are a few not so great strengths, as you can imagine. So one of the things is, of course, which is probably very visible, is the storage intensive, because the shadow cells that you need to maintain, they double the amount of space requirements. And the additional lookups will also, for example, there are cases where when you try to read a data and you don't find that it's actually in progress, then you have to actually go and check the commit table, because the transaction is committing probably has finished the conflict detection, but it has not really finished updating all the data that it has changed. And so it requires sometimes 2 reads, and and hence it's really sometimes when you have a producer consumer model where there's someone is producing and to queue, and someone's like polling for new data, you'll always you'll have this additional frequent lookups to the commit table. And replication has not been implemented, and security and multi-tenancy is a bit of an issue here, because all the clients actually have need to access the commit table, and so that's a bit of an issue. So just to summarize, here are the kind of differences between these 3 different approaches. And here are links to all of them are Apache incubating projects, so they would really welcome your contributions to the projects. You're welcome to try that out as well. And just want to give a credit to the Trafodion team and the Omid team for their help to put together this talk. So thank you so much. If you have any questions, I'd be happy to answer.
Questions?
So I found. Thank you. There was a mention on one of the earlier slides that Trafodion was inspired by HBase or something like that.
Yeah. The HBase transaction regions.
Trafodion is actually non-stop SQL from Tandem, which replaces the storage layer with HBase. And non-stop SQL, just so you know, was based on Ingress. So the code base in the architecture actually go back all the way to 1976. And there's good and bad about that. That obviously you guys are aware of, but that's a different topic.
Sure, thanks.
Edward Bortnik of Omid team.
Oh.
So yeah, just wanted to point out that the use case that you were talking about when the retrieving data that has not been committed yet requires a double read. It's actually a very rare case in production scenarios that we see. It happens quite infrequently. And the other thing that you've mentioned about getting rid of the commit table and actually distributing it, embedding it in the data itself, we have an experimental patch that does exactly that.
Oh.
Okay, so that reduces the latency a lot under high loads.
Awesome.
Okay, thank you very much.